Okay. Fourier series. So we're on a new chapter now. Steady frequency domain. I know it seems like almost every week we're on a new chapter in this class. It's so fun.
Knock it off.
Never. We have 2 weeks for this chapter, but it's also twice as long. So, yeah. But we're going to finish it up by spring break is the plan, and we'll come back, and this will be the last chapter that will be tested on the week we come back. Okay? So that's the plan, generally. What?
Of course, Fourier series.
Fourier series. So those of you who are in my instrumentation class last semester, you're going to be like, oh my God, this is very familiar, because we also did this in that class. So, if you know somebody who was in that class and who's in this class, then I'm not going to point them out. Maybe I will. They might have some insight on this stuff. So, no.
We really don't.
So, the idea with this chapter is that we're going to move over into, we've done a lot of different modeling techniques, different types of models that we've created, transformed among them, learned how to develop models from different types of diagrams like linear graphs and schematics, and we've even looked a little bit at block diagrams, electrical circuit diagrams, free body diagrams. I mean, we haven't drawn a lot ourselves, but we know those. There's a lot of different diagrams we could develop these different models from, right? These differential equation models, these transfer function models. So far, we've focused on what's called the time domain, which is to say things that happen in time, functions of time, okay? Which, at the end of the day, is what we care about most of the time. But there's a whole world out there called the frequency domain. And thinking in terms of the frequency domain is really, really helpful. And we're going to sort of build up our understanding of the frequency domain through a sort of series of topics that introduce us more and more to it. It's hard to describe it at the beginning before you see some of the parts that go into it. But it will become clear. And I'll try to sort of make a statement up front, which is probably pretty opaque. But the idea with the frequency domain is that we can think of functions as being composed of many, many sinusoids at different frequencies, okay? If we think of a function as that, then it excites a system at those frequencies. If it's an input to a system, that signal, that function, it's going to excite a system at those different frequencies, okay? And a given system is going to be maybe more responsive or less responsive to different frequencies that are frequency components that come in through the input. So the response of the system is not just dependent on, for instance, where its eigenvalues or the roots of its characteristic equation are. It's also dependent on how it responds to each of these frequency components. And you could really think of it as being another way of looking at how the system responds. Thinking of it in terms of how does the system respond to this given frequency? Now, at first we're going to think of an input as being just a sinusoid. So we'll really start there. But actually, at the very beginning, we're going to foreshadow by introducing Fourier series, composing more sinusoids into a single function. Okay, and how to think about that, how to break it down into the sinusoids, how to build it up into the function from the sinusoid. So that's how we start. So we're starting by thinking about a function in terms of its frequency components. So let's do that. And the mathematical apparatus that gives us that capacity is called the Fourier series. So Fourier series are mathematical series that can represent a periodic signal. So there are aperiodic signals, and then there are periodic signals. So there's a space there. So periodic. Aperiodic means not periodic. Okay? So Fourier series represent periodic signals as sums of sinusoids at different amplitudes and frequencies. So, like I said, we can think of a signal as being a bunch of, composed of a bunch of sinusoids at different frequencies. And that's what the Fourier series does, specifically for periodic signals, so ones that repeat themselves over and over again, right? So a sinusoid happens to be periodic. A square wave is periodic. Triangle wave, sawtooth wave, these things that repeat forever are periodic. They're useful for solving for the response of a system to periodic inputs. So we will talk about that. However, they are probably most important conceptually. They are our gateway to thinking of signals in the frequency domain, that is, as functions of frequency, not time. To represent a function as a Fourier series is to analyze it as a sum of sinusoids at different frequencies. So we denote those frequencies as omega sub n and amplitudes a sub n. And you might say, isn't that our natural frequency notation? It is. Is that confusing? It is. But n is an index here, but this is so ubiquitous in Fourier series. When you guys look on Wikipedia or wherever, they're always going to use n. So I'm going to use n just for that reason. But it does make us have to recognize when omega shows up with sub n, you have to look at the context. Is this a frequency component of a Fourier series? If so, it's denoting a different frequency for that, one of the frequencies. So omega sub 1, omega sub 2, omega sub 3, it's omega sub n. When it's showing up in the context of a second order system analysis, it's the natural frequency. So it's tough, but we're very much overloaded on our symbols. And so it not only has a frequency, but it has an amplitude as well. So each of these sinusoids has a frequency and an amplitude. So you can think of when you have a sinusoid that makes up a big part of the periodic signal. So you had a signal that's like this, and say this is actually periodic and not random looking. You see that there's some sinusoid in here that is pretty dominant, right? Pretty big. That AN, that amplitude, would be large. So whatever frequency that corresponds to, maybe this is like omega 7 or whatever, omega whatever it is, A7 would be large to represent that because it's dominating the signal, okay? Its frequency spectrum is the functional representation of amplitudes AN versus frequency omega n. So you could think of like this one's got at omega 7, we called it, omega 7, it's got a big AN. So if you're thinking of mapping it out in omega, we've got omega 1, omega blah, 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 but let's say we got up to omega 4. I'm skipping 3 here because I'm trying to get to 7. Omega 7. Say these lower frequency ones, maybe they didn't have much going on. Their amplitude, so I'm going to plot AN here. The AN's like maybe small, maybe small for omega 4. Maybe for these intermediate ones also small, It could be 0 even. And then for omega 7 though, this one would be, AN would be large. Okay, so we could think of this as in the frequency domain, and we call this the frequency spectrum. And we start thinking like this. We start thinking of like, what does the frequency spectrum look like? And we'll talk more about the spectrum a lot. So one of our new buddies. Let's begin with a definition of the Fourier series. So I think we got it like conceptually, hopefully, but now we come to the definition, and yeah, we've got integrals, but it's not so bad. So the Fourier analysis of a periodic function y of t is, for n a positive integer, period t and angular frequency omega n which we define to be 2 pi n over t, which is to say the frequency of, so the angular frequency of a single period of fractions of that period then. So if you continue to have n increase here, notice that these frequency components are all multiples of this first frequency component, which is 2 pi over t, the period of the signal. So we say an and bn are very similar. You put your function y of t inside the integral, and you multiply it by cosine of omega nt, and you integrate it over one period. And in fact, I wrote this as being over the period negative t over 2 to positive t over 2. Any period, this is valid. So as long as you integrate over one period, you're fine. Now, this gives us an components and bn components, an an and a bn for each frequency, right? And so this is called Fourier analysis. We're breaking it down into the components. We're finding out at a given frequency, how big is this an, right? So, for instance, in this case, the an would be big for omega 7 here. And that would just come out of the integral. We didn't have to know that just by looking at the graph. We can find that from calculating this integral. Now, the Fourier synthesis of a periodic function y with analysis components an and bn corresponding to omega n is this sum. So, ignoring this constant out front for a moment, we're summing up the an times the cosine and the bn times the sine of these omega n terms, omega nt terms. So, these are, like, we're in 6.1 and 6.2, we're doing the analysis, and in the synthesis, we're kind of undoing the analysis. We're recomposing, reconstituting the original function, right? Y is here and y is in here, right? So we're in the one, we're decomposing it. So this is sometimes called a decomposition as well in Fourier analysis. We're decomposing it. And then in 6.3, with the synthesis, we're composing it again. We're reconstituting the function. Okay? So it's just, this function is just a sum of all of these sinusoidal terms, right? With different frequencies and amplitudes. Okay, so that's the trigonometric formulation, which is the one that is probably the most accessible because it's very obvious that it's in terms of sinusoids, right? We're summing sinusoids. Let's consider for a moment the complex form of the Fourier series, which is analogous to this definition. It's equivalent, but it's presented a little bit differently. So the Fourier analysis of a periodic function y of t is, for n of positive integer including 0, period t, and angular frequency omega n equals 2 pi n over t. So there's only one of these. The complex is what goes from negative infinity to positive infinity in terms of the terms. So you can decompose this into C's having indices that are positive and negative indices. So not just positive indices like they were for an and bn. That's why there's a plus and minus. So in this one, instead of doing two different integrals, you do one. And instead of using cosine and sine, the trig functions, you use a complex exponential, actually an imaginary exponential. So this is, remember the Alamo? No. Remember that we have Euler's formula, right? Euler's identity that allows us to go back and forth between a complex exponential form of something and a trigonometric form. So when you see this, you say, oh, okay, this is just sines and cosines. E to the minus j omega n t, just sines and cosines in there. but mathematically this actually works out a little bit nicer. It's a little bit easier to integrate with an exponential. You guys have, learned that when you were in your calculus class and you had an integral that had an exponential in it. It was a lot easier to work with than if you had to deal with trig functions, which were a lot more pain. So it's useful mathematically, and we will use the complex form quite a bit as well. The synthesis is actually pretty easy too. You just sum these up. You just sum these up, all these complex terms. So a couple more definitions. I'll do the example next time, but I'll finish up this little definition here. So we call the integer n a harmonic. Okay, this is an important term, harmonic, and the frequency associated with it, which is, we already observed, is 2 pi n over t, we call the harmonic frequency, okay? There is a special name for the first harmonic, okay? When n equals 1, which is just 2 pi over t. It's called the fundamental frequency. It's the frequency of the entire periodic signal, right? It's the fundamental frequency. It is called this because all other frequency components are integer multiples of it. So notice that when n is equal to 2, 3, 4, you just have an integer multiple of that fundamental frequency. It is possible to convert between the two representations above. So this just gives you the formula for going from the trig form coefficients to the complex, or from the complex to the trig. We don't use this a lot, but it's good to know that this is the transformation. And then another definition here is the harmonic amplitude, which is that Cn is equal to the square root of an squared plus bn squared, which is 2 times Cn times. So Cn and C minus n are just complex conjugates of each other. So it works out nicely to multiply them together and get a real number. So give me just one more minute, and then I'll let you guys out. A line spectrum is a graph of the harmonic amplitudes, so we just defined them, as a function of the harmonic frequencies. Following illustration demonstrates how sinusoidal components sum to represent a square wave. So in time, we've got the square wave, and it's like a little bit wiggly because we aren't taking all of the components, all the frequency components. And then you can think of this frequency dimension as describing the frequency domain way of thinking about this signal. It has different amplitudes. So this fundamental frequency is pretty dominant in the square wave, right? Composes a lot of it. And then these higher frequency ones, they help tighten up that square, right? So it starts out looking just like a sinusoid when you add the first component. You add the second component, it gets a little bit more like a square wave. You add the third component, it looks a little more like a square wave, and you keep adding them, and it looks more and more like a square wave, okay? So computing the spectral components from this example is going to be what we do next time, okay? All right, see you Friday.